Okay, I think, Susan, what do you think? I'm going to go ahead and get started. I think we're at about close to our max of who we had registered for today. So thank you, everybody. Welcome. It is Ask a Scientist. Today we're talking about atmospheric science and dispersion with Dr. Jessica Osuna from Lawrence Livermore National Laboratory. I'm Sally Allen. I'm the Executive Director of the Livermore Lab Foundation, which has been, we'll talk about that a little bit later. But we basically work in partnership with Lawrence Livermore National Lab to try to work to inspire the next generation of scientists and engineers, much like many of you in the audience today. We are thrilled to have our speaker today, and we are this is part of a series that we've been producing in partnership with the lab and with the Livermore Valley Joint Unified School District. So this is the third in a four-part series, and I just want to introduce a couple of my colleagues today. Susan Houghton is working with the foundation, and she's been instrumental in helping us organize these meetings, and she's going to be helping monitor and review the questions that come in during today's talk. So thank you, Susan. From the school district, we have Kevin Greer, who's our Director of Curriculum and Instruction. Hi, Kevin. We may be joined by the Assistant Superintendent, Mike Biondi, at some point. I don't know if he's on the call yet. If you are, Mike, welcome. And from the lab, we have Nadine Horner. Hi, Nadine. She's on the Community Relations team at the lab. And of course, we have Dr. Jessica Osuna, who I need to unmute. Hi, Jessica. Is that working?
Hello.
Thank you. Thank you. We're so excited to have you all with us today. So let's go ahead and get started. We can go to the next slide. Just quickly, as I mentioned, this is the third of four Ask a Scientist events that we've been hosting. And we had a couple last week, and we've got one more coming up this week on Thursday. If you haven't signed up yet, you're more than welcome to. We'll be building edible aquifers with Monique Warren from the lab if you're interested in environmental science. So we're excited. And our website was on there too for you. All the information is there, and we'll show it at the end of today as well. Some quick housekeeping. We have muted everybody for now, just for the sake of being able to focus on our speakers. But if you have questions, we really encourage that, and we'd love to hear from you. So please use the chat feature at the bottom of your screen, and Susan will be helping screen those questions that come in. If you would love to have a chance to ask Jessica yourself by video, by all means, we can do that too. So please direct your questions throughout the talk to Susan, and we will make sure we'll get to those. We're going to start with some of the questions that you all submitted in advance, which is fantastic. So thanks so much. We are also recording today's meeting, and we'll be sending out a link to the full recording at the probably next week. So let's get started. We today, again, have an amazing scientist from the lab, Dr. Jessica Osuna. She's an atmospheric scientist, and she's going to share a little bit more about what that means. She lives in San Leandro, not too far from the lab, and she's been there for about 8 years. And she's been at the National Atmospheric Release Advisory Center for about 4 of those years. And she lives with her family. I think for those of you, hopefully, who watched the video in advance, you got to see some of her family members as well, and we may get to say hi to them today as well. So why don't we get underway? Jessica, you can share a little bit more about who you are and what you do at the lab, and we'll get started.
Awesome.
Thank you. Welcome.
Thank you. Thank you so much for having me. It's really fun to see some faces again, because when I'm at the lab, I have the joy of hosting a lot of high school tours that come through usually, and that's a really fun part of my week. So my favorite part about that is getting to talk with the students and hear the types of questions that you have and how you relate our work to your daily life. So absolutely, as she said, you know, pepper me with questions, and I'm happy to have a conversation, and I don't want to spend an hour just talking at you. So definitely speak up, don't be shy. To give you a little bit of an idea of who I am originally from Illinois, and I first studied atmospheric science. And that was because I liked watching the thunderstorms and the tornadoes. And here's our dancer. I loved watching all of the cool weather outside, and I was interested kind of in how things all work together as one big system in the world. So While I was studying atmospheric science at the University of Illinois, I was lucky to have a few faculty members that helped me to think a little bit broader than what I did before and start thinking about how different parts of the Earth interact. And so I got interested in looking at how the land surface and the atmosphere interact. And that's how I ended up studying what I studied in graduate school, which was exactly that, looking at how changes at the surface of the Earth result in changes in the atmosphere above it. And so when I was doing that work, I was looking at how you can create maybe more or less hydropower. So when you have water flowing through a river and you use that flow to charge a turbine, and we were looking at if there's a big drought and you have much less water, you know, how can we predict that change? I was looking at when you change an ecosystem at a surface, how do you change the amount of wind energy that you can generate above? So those types of things. But after a few years, I got really interested in working on a very specific direct mission that serves the public. And so that's how I ended up at NARAC. And so if you had the opportunity to watch the video, basically what NARAC is if there's ever a release of dangerous material into the atmosphere, we use a whole set of models to predict where that dangerous material is going to go, how it's going to behave in the atmosphere, and what the impacts on the people at the surface are going to be. And so I really enjoy that work because it's a very clear mission. We work on a team and it's a really quick, fast-paced job when something happens. I also love that I'm taking all different parts of science and bringing them together to really serve the public. And so in addition to atmospheric science, I learn about all different fields of science and integrate them and work with team members that are experts in other areas, and we kind of all bring our backgrounds to the table to answer questions. So some of the things I think that I mentioned in the video is we responded, a lot of you might be too young, but you may have heard about the release at the nuclear power plant in Japan. I believe that was in 2011. And so I wasn't at the lab then, but NARAC responded to that and was operating 24 hours a day for about 6 weeks, supporting both foreign governments and obviously the US interests. And so that was a big one that we responded to. And there's a lot of other things that we support that maybe don't make the front page of the newspaper, but we're here supporting and ready at all times. So with that much,
thank you so
we've generated some food for thought for questions.
Yes, and I should add, I'm pretty new to my job and learning about the lab, and I went on a community tour, and NARAC was a part of that. So I think that that might be an option for folks that are interested. Once we get through the shelter in place down the road, what you hear about today, it's really a cool place to get to visit and to see how many global, not just local and regional, but really global events you've played, or the NARAC has played a role in. So thank you. Okay, we'll go ahead and get started. That kind of leads us into just sort of an opening question in addition to what you were just mentioning. Can you offer other examples of projects or that NARAC has been a part of or been instrumental in helping address anywhere in the world that people might be?
So one that a lot of people might know about is it 2 years ago already, there were fires in Southern California. And we don't usually respond to fires because there's not usually the risk of having radioactive material dispersed into the atmosphere, right? Usually it's biomass that's burning. In this particular fire that occurred east of LA, it was burning over a site called the Santa Susana Field Laboratory. And this is a site where many, many years ago, NASA, the Department of Energy, and the Department of Defense used to do some experiments. And from that, there was some contamination left in the soil. And the US government is working on rehabbing that site and taking care of it, and they're being good stewards of the land. But what happened is the fire started right by that area and burned across the area. and the smoke was lofting all across the LA Basin out into towards the ocean. And it just so happened that where that fire was occurring was near places where a lot of famous people have very, very, very expensive homes. And it was on a Friday evening, and I was on call, and I was getting ready to leave work. And all of a sudden we find out that Kim Kardashian is tweeting in fear about this fire that's going over an old field lab that was a Superfund site at the EPA. And so Kim Kardashian has a very big audience. And so things revved up really quickly. And so instead of going home and doing whatever I planned on doing on a Friday night, and that's fine, that's my job, I got to spend the Friday evening eating pizza in our operations response center and putting together some estimates of what the worst possible case scenario could be, just to basically comfort the public in knowing that, you know, this fire was not actually proving to be such a risk for the public. You know, we don't expect this material to be able to get lofted up. And we did end up having to send field teams down into a fire to make measurements and prove the zeros, right? Because in science, a zero is just as important as a positive number. And so that was one recent response that we participated in that has kind of a funny backstory, considering that it was basically Kim Kardashian that, that got us started.
You don't want to get her Twitter followers.
So that was one. Another one that a lot of people didn't hear about, but that's pretty interesting. It was a worldwide effort to understand a few years ago. All of a sudden there was this isotope called Ruthenium 106. And that particular isotope is only made in very particular processes, sometimes associated with the nuclear power plant, medical devices, things like that. But you don't expect to detect this particular isotope in the atmosphere. And there's a network of sensors around the world, and all of a sudden there were these detections. And so there was a lot of worldwide effort to explain where it was coming, you know, what was going on. And so NARAC was heavily involved, and we produced very highly regarded reports about that particular release. And so you can find more information about that just by kind of Googling Ruthenium 106 in Europe or something.
Great, thank you. So Jessica, what does your typical day look like? I mean, are there teams that are monitoring the air 24/7, and or do you just sort of come in and have a regular day, or what does that look like?
So in general at NARAC, every week we have two people like myself, two scientists that are on call. And so when you're on call, I should have had it. I don't have my pager. I think my daughter's online. Maybe she can go grab me my pager. When you're on call, I still carry my pager, and if something happens, we'll get paged. But otherwise, you know, at the beginning of the week, we're monitoring the weather. So we'll do a briefing every Monday and every Friday about the weather. Because we want to know at any given point if something happens, we want to have a general idea of the weather in different parts of the world that we're interested in. Thank you, dear. Here, show and tell. How many of you have seen one of these recently? So this is my pager. I know, I can see, I'm glad to see some of the video, you guys shaking your head. We actually do still use these, and they're much more reliable than phones if there were to be an incident real close by here. So we'll monitor the weather in certain locations so that we know what's going on. We receive over 1 million observations a day of weather from around the world from public networks. We also receive terabytes upon terabytes of forecast data. So we look at those things. In a regular day, we'll have a lot of people that we work with around the country, other nuclear physicists, people at nuclear power plants, things like that, that are working on different things that will call us in and ask some questions. And so who's ever on call will field a lot of those questions. We spend most of our time doing exercises where we pretend like it's been a really bad day for somebody somewhere and how we would respond. And that way we get really used to working with our teams. So we do a lot of exercises throughout, you know, they can range from maybe 10 people around the country to hundreds of people participating around the country. So we do those. And then we do a lot of you know, research and preparation and testing our systems and little tasks with each of the different customers that we work with to make sure everything's ready when we need it to be.
Great. That's fascinating. It's reassuring to know that there's a whole team of you working on those things on a daily basis. Let's see, Susan, how are we looking on questions? Because I can do a couple more, or we can.
No, we have our first question, and I know we're going to have many more. So our first question that's come through, Jessica, is how small of a particle can you track? And how does that size translate or compare to a virus particle?
Wow. Boy, you guys are hitting me with the hardballs from the get-go. So we can track very small particles, so under 1 micron, very, very small. And when you track a particle, it really depends on what you're using to track it. And so if you're tracking it in an atmosphere, then you need to be doing something that's collecting the air and sampling it in place, right, all the time. If you're going out later to collect samples, then you can track incredibly small particles, much, much, much smaller than what they're looking at with the virus, I believe, but I'm not a biologist. So there's other people in NARAC who would definitely be able to answer that question, who work on kind of the bio threats, but that's why we rely on a team. So I won't address that too much, but as far as physical particle size, we can work with very, very small particles let's see, so respirable particles, particles that you can actually get into your lungs and breathe, and they can get into your body, are less than 10 microns approximately. And we can measure concentrations of particles that small, definitely. So with in situ, air samplers that are collecting right there. Most of the time, though, we don't have instrumentation set up, in high density around the country. So usually what happens is we measure the material once it's been deposited onto the surface of the ground. So once a release has occurred, the material will be deposited onto the ground as the wind blows, and we'll be activating all kinds of teams that will go out to the site and measure it. And so in that case, they have some sensors that can measure the concentration on the ground, but a lot of times they're also going to collect samples and send them back to very, very specialized lab facilities like ones we have at Lawrence Livermore, and they can do a much more high integrity sampling and study of the material.
Great. If it's okay, can we ask a little more about the video experiment that you did? I'd never seen a water density tank. That was just so cool. And curious, where you got that idea, and if you had done it before, and if anyone out there had tried to recreate it at home, I'd love to hear that too.
Yeah, so I have been asked a few times to go out and speak with students, and I get tired of just speaking at students. I know students get a lot of lecturing and that, and I don't want to lecture. So I was looking for something that was a little more hands-on and fun, and I found the idea on YouTube just by Googling a bunch, and then I was able to, here we go, this is our little tank. And at first I was really not pleased, because all I was doing is I had the red water on one side, the blue water on the other side, and I'd pull it out and you'd see the cold front. But I was like, that's kind of boring. Everybody can see that. So between my kids and I, we spent probably a week trying to figure out how to do something a little more interesting. So we had all kinds of rocks at the bottom, and I was trying to show the impact of turbulence at the surface on creating roughness, surface roughness, to create turbulence and improve mixing. And so we tried that a little bit, but the tank was a little bit too small. I had my kids building little landscapes at the surface and stuff to try to do that, but I think I'm gonna have to invest in a bigger tank for that to work. So eventually, I thought, okay, well, I need a release. And because we were really sheltered in place at the beginning, this was like the magic ingredient that made it all work. And this was a little trinket I found in my son's room. So I was really glad I actually found this after I had pretty much given up and was just going to do a boring cold front. So
I assumed that was a real scientific instrument that you had in your inventory, actually.
No, I think
it worked so well.
Yeah, at their school fair, I think it was like a little trinket prize that he had gotten and hoarded it away somewhere, and I saw it and I was like, that's the magic ingredient, that's gonna work. So it was really exciting. But we went through, I had a huge cooler of water in my kitchen for about 2 weeks, because I wanted to make sure the water was room temperature. And that way you could really see the difference between the hot and the ice cold water. And so It was not a good experiment for water conservation, but hopefully that with the video, I won't have to do it again and we won't waste so much water. But every single time you do it, if anything goes wrong, you have to dump it and start over, and it's
right. It really illustrated the concept so well, though.
It was fun. I was really, really glad that between my kids and I, we kind of settled into that setup finally.
That's great. Thank you. Susan, any other questions?
Oh, what is a pager? I see that. Is that okay? I'm sorry, I just took your job.
So we have another question that's come in where this person wants to understand, do you ever have cities that hire you for like dust storms or industrial fires? There was a tire fire years ago in Tracy. Could you talk about that?
Absolutely. That's a really good question. And so when we look at, so I'm going to start a little bit back up from that question because I want to explain the difference between modeling in a city and modeling out in the middle of nowhere. So if you're out in a valley and you have the surface is really smooth, you kind of just get this nice flow field, right? You can imagine just the air kind of blowing over a valley and you can see the grass kind of just blowing in a steady wave. Once you get into a city, if you've ever watched leaves blowing around in a city or trash blowing around, you get these eddies is what we call them, right? And so as the wind whips through all these buildings, it's almost like a canyon, being in the middle of a canyon or a wind tunnel. And so it's really, really, really different to do that modeling, and you need very different models. And at NAREC, we have that ability to model in cities, and it's something that we're constantly making better because that is where most of the people live. And so one of the recent releases that we did was, or scenarios, it wasn't actually a release, is in Seattle, actually, there was a hospital that had some medical equipment and that included radioisotopes, which are often used in treatments and instrumentation. And they had a little bit of a leakage out of that instrument that caused some radioactive material to be present outside of where it was supposed to be. And so absolutely, the city called us and wanted to know, the city actually contacts the Department of Energy, and the Department of Energy uses all of these kind of tools in their tool belt to make sure that they're serving the citizens of that city in the way that they need to be served. And so in that instance, there was not an actual release out to the public, but what we were doing was constant modeling of what if a release happens in 2 hours? Okay, now 2 hours from now, and 2 hours from now. And that way we could look at the predicted wind patterns and see how they would interact with the buildings in the area and what kind of exposure any people in the area would get. And that way you could preventatively make sure that people were out of a dangerous zone and things like that. And a lot of the exercises that we do involve scenarios that could occur in a city. And so we work a lot with local fire departments and search and rescue teams and things like that to practice integrating all of our skills in a real response. Okay. So is there any other part of that question that I missed? In my
no, that was it. So we have another question that has come up about climate change.
Okay.
And do you do anything related to climate change, and what is your opinion on climate change?
Okay, so I don't think climate change really needs an opinion, it needs facts. And so being at Lawrence Livermore National Lab, there are a ton of ways that they integrate all of the facts to make a clear and compelling story. And so definitely, while I, in general, as a scientist and having worked in that field for a while, I can give you some of the facts that I know, but the experts are upstairs from NAREC, where they look at all the models that are produced and they around the world, and they look at massive data sets and do tons of comparisons between the models and the data, and incredibly complex ways to really pull that apart. And I think the evidence is clear that the climate is changing, and it's silly to deny that, because really all you're doing is denying yourself the opportunity to prepare for the future and be successful in whatever that future will look like. So for NAREC, the biggest influence of that, so we have some thought process going on about how climate change might impact places where the United States has radioactive material, whether it be an impact on hospitals or Department of Energy sites. or storage of old nuclear power plant material, things like that. So we've started to think about how climate change might impact the ecosystems where those are stored. But really NARAC doesn't, I think the only other thing that I would say we do in relation to climate change is that a lot of times when we're helping areas prepare for potential hazards, the hazard very much depends on the wind, right? On the atmospheric conditions. And so when we're trying to estimate the typical atmospheric conditions for an area, we will no longer go back, you know, so far to the data that we have from the 70s and 80s, because the climate is changing so much. You really want to stick more with like a 5 or a 10-year average for an area. And you can really see the difference if you're looking at wind speeds, temperatures, even wind directions at certain times of year. Those change a lot. And so in order to help cities be prepared for emergencies, we want to use the best data. And the best data is really looking more recently, because we know that the climate and the conditions are changing.
Okay. So we have another question about the waves that you mentioned. What kind of waves are present during an earthquake?
During an earthquake.
Mm-hmm.
So I don't really work much with earthquakes, but is that, I'm not sure what that is referring to. Let's see, what kind of waves are present in earthquakes? So I don't really work with earthquakes. So I would leave that question up to somebody who is a seismologist, which there are plenty of those at the lab.
Okay, we have another question that's come in regarding COVID-19. You know, are you doing anything related to COVID-19 and, you know, being able, when people talk, it coming out and measuring anything that's in the atmosphere?
Mm-hmm. So no, we are not involved in a response with regard to COVID-19. I will say the closest is that at NARAC, we focus on radioactive and nuclear material, but we are definitely capable of also measuring, modeling both like bio threats, biohazards, like in a subway or in a city or things like that, or other chemicals. And so if there was a threat of maybe somebody figuring out how to bottle up coronavirus and release it at some large public gathering, we would be able to support that response with some of the capabilities we have. And that would be with members of our team that I mentioned before, that'd be more experts. But in general, right now, our posture for COVID-19 is that we rely on the people who are really in the weeds and studying it to make sure that we're able to keep our team safe from it also, because if there were another disaster that were to occur during this pandemic, we don't want to have all of our team descend upon the scene or descend upon our operations center and get each other sick. So they take very, very good care of us, and they encourage very good habits and social distancing to make sure that we're always ready to respond despite a threat of a pandemic.
Jessica, how many people work at NARAC, and how do people access the services there if they're not part of the lab? I mean, are you responsive to any kind of requests that might come in, or how do they respond to requests, I guess, for support for the services you provide?
Yeah, so at NARAC, there's, if you look at the big picture, there's about 40 people split between like computer programmers, IT people, scientists like myself, and then the researchers also who help to develop the models that we use. So in total, it's about 40 people. A lot of people on the periphery who will be pulled in when we need them based on certain responses. And how people access is when there's, you know, not everybody has radioactive material, hopefully, and nuclear material. And so the people who usually have this material will know exactly how to contact us. We have a phone number that's monitored 24/7 for somebody to call us directly. In general, usually those requests go through the Department of Energy, the NNSA, and then get routed to us and any other teams that need to be activated based on the information. Every once in a while, we will have, you know, somebody who's out, and this is actually real. During an exercise, we got a phone call and somebody was out in the middle of nowhere and on the side of the road found a small container that had a sticker with a radioactive symbol on it. And so they kind of just called you know, Googled online to see who they could call, and they ended up calling us, and ends up, I think it was just a sticker that somebody bought on Amazon and stuck it on some random container, and everything was fine. But we did actually have to send out teams to double check and make sure everything was okay. And we ran some simulations to make sure that if it was not okay, you know, who would be impacted. So usually it's a phone call. With a lot of our collaborators that we work with, they can also go onto a website that we have and give us some very basic information about the situation. And then if they do that, my pager will go off. And then we'll get right on and give them a call back and immediately start addressing the issue.
That's impressive. I mean, 40 people, I was expecting you to at least say 100 or more. I mean, based on the scale of what you guys cover and everything.
And I think the actual team, so there's about 7 scientists like myself that rotate through the on-call staff. And then I think probably about the same number of IT people who rotate through the on-call staff. So it's not a big team, but it's people who, once you get there, you stay there, because it's a great place to work.
Yeah, I'm sorry, Susan, I'm jumping in. I'm fascinated by this subject. So I keep coming up with new questions, but do you ever have interns? I know this year the internship program at the lab has been affected, but a little bit, but for people thinking down the road into college, you know?
Yeah, for sure. So in the past, most of the interns have been part of the computer programming side, where they help us to develop some of the websites and computer tools that we do. But I'm really excited about the opportunity to mentor young scientists also. So we have quite a few projects that students can work on in the sciences also. So we, for example, might look at different ways to process measurements of the wind to be more representative of what we're looking at. And so different programs with all that massive amount of data we bring in, how we can assess that a little bit better to use it in our models. So there's a lot of different opportunities for sure.
Cool, thank you. Okay, I understand we have more questions streaming in, so I'll turn it back to Susan.
We do. We have some very active students, all of whom are too shy to come on and do their own video, so I'm going to ask for them. But Colleen wants to understand how much the Earth weighs, and if there are clouds in winter, when is it too cold for the water to stay a vapor?
Okay, so we know what temperature water freezes at, right? And so that's 32 degrees Fahrenheit. Water will freeze. However, in the atmosphere, there's all kinds of other dynamics that go on that allow you to have what's called supercooled water. And so in order for water to actually freeze, a lot of times what you need is like a little dust particle or something for that water vapor to interact with to turn into a particle. And so when you have a really clean atmosphere, or when you're up high in the atmosphere a lot and there's not a lot of those dust particles, so the actual term is called a cloud condensation nuclei. And so you can look that up also if you're curious about what those are. And that helps, even when you have super cooled water, it will help to get it to actually condense into a raindrop and then fall and, you know, turn into snow. And so the actual temperature that can occur at will vary based on how much cloud condensation nuclei you have to go from vapor to solid. Boy, how much does the Earth weigh? That's tough. I don't know. What's that? Was somebody going to speak up?
No.
Oh, darn. I thought somebody was going to take it for me. That's a really hard question. I don't know.
I think we should give back to the students to assign it and tell us what happens. So we have another one. Matthew wants to know if you could go into a little bit more depth on how you use your computer models.
Yes, I would love to. Okay, so we have a lot of computer models. And actually, this might be a good chance. There's a picture that I will show you. But basically, so we have to start from the very beginning of a release all the way to the end. So if you wouldn't mind going to slide 15 and pulling that up.
Nadine.
So the first model that we have to have is of the atmosphere, right? So we have to create the conditions where a release is actually occurring. And so what we'll do, the first step is that we'll figure out the location where a release has occurred. and we'll pull all of our all of our observations or our weather forecast and from that area. And we ignore everything else in the world, right? Because we don't need to model all of that. So that first picture on the top left there is showing, okay, we have information about the whole world. When a release has occurred, we zoom down into a very particular location and we pull out all the information about what the land surface is. We pull out the information about what the current weather is expected to be, about the population in that area, the building density, any information that we have in our databases. And from that, we create what's called a flow, what I call a flow field, right? So that second box with the arrows, you can imagine that kind of like my density tank. So we set up this domain, which is like an aquarium in our model, and we're only concerned about the area that might be impacted by this release. And once we do that, we create this flow field that is describing kind of in better density all of the phenomena that we observed through our different measurements. And so once we have that, now we've got our flow field. And in that flow field, something is happening, right? So we need to know what's happening. And so on the right, that big fiery, ominous looking cloud, right? That's one scenario of what could happen. So then we have all of these models that help us to understand what it looks like when something gets released in the atmosphere. If it's a nuclear explosion, that looks like the picture, right? If it's a little bit of a source leaking out through an exhaust pipe in a building or something, you know, that's going to be a small little leak coming out, you know, much slower, much closer to the surface. It's not going to blow real high. And so that's a different kind of model. If it's a fire that had a component in there that was radioactive, that's going to have some lift from the heat, but it's not going to look like that cloud. So we have all different kinds of models that can help us describe how this stuff is getting in the atmosphere to start with. Because if you've flown in an airplane or if you've watched kind of flags or hot air balloons, you know that the wind will change directions, will change wind speed as you go up higher. So it's really, really important to know how high in the atmosphere a release is occurring so we know which way it will go. So now we've got our, you know, our aquarium, our flow field, and we understand where all of the material is starting because we have our model that, you know, mimics a fire or an explosion or a leak or something like that. And when you put it all together, we have what's called Lagrangian models. And this is really silly, but the way I used to remember what a Lagrangian model is because this is really cheesy mom joke. Lagrange has the word kind of range if you look at it. And I used to think of Home on the Range and like something floating along the range. So I remember, okay, in a Lagrangian particle model, you're following a particle. So we get kind of the qualities of whatever was released, and we assign all of those qualities to little ping pongs, basic ping pong balls that we release in our aquarium, in our flow field. And so we'll set how dense those are. So if those particles are rocks, they're gonna fall to the bottom of the aquarium, right? If they're tiny, tiny little specks like fish food, they're gonna float to the top. And so depending on what was released, we describe our little ping pong balls similar to the material that was released, and we let them go through the flow field and we follow them, right? Because it's a Lagrangian model. So we follow where they go. And at any point in time, we can pause the model and we can say, okay, where is all of our mess? How concentrated it is? Is it in the atmosphere where people are breathing? Or how much of it has fallen onto the surface where people are standing? And so then we have another model that takes all of that information of the concentration of chemicals and it calculates the impact on people or the impact on food or the impact on the water supply, things like that. So it's a whole chain of different models that use different information to go from what is the wind doing outside, what just happened, and how does that impact the people on the ground. So it's a long answer, but it's a really long process. And the most amazing part of it is that we can do that all in less than 15 minutes, like that, because it's important to do that, right? And to help people right away.
So, Dr. Jessica, I was Googling how much the Earth weighs, and I have an answer. So I am just going to give you the numbers and let everybody understand how many pounds this is. It's 1317 and then 22 zeros after that. There we go. And in the chat, Margot put that in.
That's awesome. Thank you.
Now
I
we
would
all
not
know.
have gotten there.
Thank you, Margot, for putting it in the chat.
Wow.
So Sally, we have a few more questions that I want to make sure we get to from students.
Great.
Madison said, I learned that trees and oceans absorb carbon dioxide, which means that helps prevent climate change. But I also learned that 1 particle of methane is equal to 23 particles of carbon dioxide. So is there something that absorbs methane?
That is an awesome question. And so the concept that she just described about how much certain chemicals contribute to global climate change, that's called the greenhouse gas potential. And that was actually coined by my undergraduate advisor. He wrote the book on the primer for all of these different chemicals. And so, yes, that's awesome that you got to that information and you were able to parse that through. One of the main sources of uptaking methane or releasing methane, where it's stored, is in like bogs and tundra. So far north ecosystems that usually are frozen, they hold a lot of methane, and they're not exactly taking it up all the time, but they're holding it down there. So it's a big storage tank of that. And so that is an impact of climate change, is as the ground is thawing more, it's letting a lot of that out. And there are people at the lab in a facility called CAMS who study that quite a bit. Taking up methane. So I don't know off the top of my head of natural processes, but I know there's also people at the lab that are studying different methods of carbon capture, which is where you kind of do this thing where you filter and kind of siphon out of the atmosphere some of these chemicals that are more harmful. So I'm guessing that they're working on that, or that they've come up with a way to get some of that, but I don't think it's well enough developed to actually be implemented on a broad scale yet. But
we have another one from Julian. How does the atmosphere trap air on the Earth?
Gravity. So gravity impacts everything right on Earth, and so we just talked about the mass of the Earth, and because it's so massive, right, it has a strong pull of gravity, and so that's what's pulling all of the air particles towards us. Now, once they get towards us, they get trapped kind of down towards the surface because there's a lot of layers in the atmosphere. And so we exist in the lowest layer, which is called the troposphere. But the layer above that is the stratosphere, and there's a really stable layer. So it acts like a lid, and it's hard for air to circulate beyond that layer. So once we get all those particles that are brought down to the surface because of gravity, they tend to get stuck there for a while. And if they have some reason, like some volcanoes have enough force to push air particles up into the stratosphere, that lid between the troposphere and the stratosphere, the first layer and the second layer, kind of tends to keep them up there for a while. And so they don't just float away into space though, because gravity still acts. That lid doesn't stop the impact of gravity. So air particles generally will, depending on their size, will sink towards the Earth because of gravity, but there's also layers that they might get trapped in within that.
Sarah wants to know, how long does it take a meteorite to hit the Earth? I'm assuming once it enters the atmosphere.
Yeah, so that depends on the trajectory, right? So if you have my Earth, you might have a meteorite that's coming right across like this. And then it would be a different time versus if it's coming straight at it. And I think also there are meteorites that are going in all different paths around the Earth all the time. So of course, the time it takes will depend on where it is, where it's entering, the speed. A lot of times it's also the size, because a lot of meteorites, once they get into the atmosphere, that change in conditions from being in outer space will cause them to burn up, and they may not even hit us, or maybe it'll be just a tiny, sprinkling of particles that you don't even notice are coming down and kind of littering across the surface of the Earth. And geologists and other field scientists can detect that. That's the source of a lot of the isotopes we have on our Earth. If you're talking like a really big meteorite that's going to come and be the headline of the news story, it's going to be pretty quick, probably on the order of minutes. I'm guessing that there's other people, again, at the lab, and I'm so lucky to know so much about what people do at the lab because there's a lot of cool stuff, who study that exact phenomena. And if you watch some of the other videos, I believe there's a video even about how we prevent it from hitting. So if we know there's a meteorite coming towards the Earth, well before it gets into the atmosphere, we have things that we're studying to actually change the path so it doesn't get to us. So that's also incredibly cool work that I just get to listen to as a fan.
Yes, just a reminder, we had that speaker last week on planetary defense, and we did record that session, so it'll be on the Foundation's website next week. So.
Perfect. Yeah, you guys should watch it. It's such cool work. It's like a sci-fi movie. It's really awesome.
We have one more question right now. What would happen, this is putting your philosophical hat on, if the Earth spun the other way and the moon did not exist?
If the Earth spun the other way, we would have sunrises in the west, and I would be very happy. No, actually I wouldn't be, because I much prefer sunsets. But we would have sunrises in the west and sunsets in the east. And if there was no moon, then we would also have a lot of difference in the tides, right? So we know the moon has a lot of mass. I didn't realize this was going, I apologize. The moon has a lot of mass, and so there is also gravity from that mass. And so that gravity and where the moon is in relationship to the Earth provides a lot of the changes in the tides that we see. That's what drives it. And so we would definitely have changes in our tides from that, from not having a moon. The other thing is that, let's see, so the Earth, the main thing that influences kind of our seasons and the northern and southern hemisphere is the distance of the Earth from the sun, this is again, and the angle of the Earth. So as long as the angle of the Earth's rotation wasn't changing, just the direction, I wouldn't expect that it would be huge impacts on the seasons and things like that. But of course, we would have, so right now if you watch the weather and they say we have a low pressure center, and so you see the flow is going counterclockwise, and that's usually associated with storms and things like that. The reason that that flow is counterclockwise is from what's called the Coriolis Effect, and that's because as the wind flows over the Earth and the Earth is spinning, there's a little bit of drag, and it tends to pull the wind in one particular direction. And so you would have probably your low pressure centers actually occurring clockwise instead of counterclockwise from the rotation of the Earth. So that would be fun. That would throw us all off.
Thank you so much, Jessica. I think you can see you have sparked a lot of curiosity in the students today. The questions keep coming, but we don't want to take you too far afield from your area of expertise. Before we wrap up, maybe just one more question for you. And you addressed this a little bit in your video, but what advice can you offer to students that are on today that were interested in the subject matter and might want to learn more, or someday be in your shoes and work where you're working? Based on your journey, what kind of advice could you offer?
Yeah, I think the best advice, there's all kinds of advice about what classes to take and this and that, but I think the best advice is to never sit in a class and go, oh, I just need an A, I'm never going to use this. And I'm saying that I did that. Of course, we've all done that, I'm sure, at some point. And the main thing is that, the real world is a complex place, and there are so many interactions, and it's a really cool thing to see how whatever you're interested in interacts with all these other fields. And so when you have the opportunity to learn something, it's really important to take that opportunity, because you never know when it's going to come in useful. So for example, I do atmospheric science. I'm very interested in the science. There's a lot of people who do policy behind the scenes, and that wasn't my thing. I was happy to let somebody else do policy, but I'm glad that I paid attention a little bit to how policy is made, because that impacts things that I do on the job. Or even psychology, right? So when you have the threat of a release, you need to understand how people tend to respond, and that helps you to prepare better in that situation. So I think regardless of what people's interests are, it's really important to not, you know, slough off everything else, because the world is an incredibly interconnected place and it's fun to find those connections later. So that would be kind of the biggest, broadest level of advice. For somebody interested in atmospheric science specifically, I would say computer programming is really important, and it's really powerful, and it really makes you better able to answer the questions that you're interested in a work environment if you're able to do some sort of coding and understand computer programming a little bit.
Terrific. Thank you so much for that. We feel so lucky that we had you with us today, and thank you for your time. We're going to wrap up here. Thank you all for joining us today. And before you leave us, just a reminder, the Livermore Lab Foundation was hosting today's event, and you can learn a little bit more about us online. We have a website, and we also have a newsletter. If you're interested in signing up to follow for future events, we'd love to have you. The information's on the slide there. And just please continue with your curiosity and pursuing science, and join us on Thursday at 1 o'clock for the next Ask a Scientist if you can. Thanks everyone, and have a good afternoon.
Thank you everybody for joining, and hello to my nieces in St. Louis.
Oh, nice.
Dr. Jessica, you can stay on the line.